let's look at gain of a linear circuit as a function of frequency. So we'll look at the phasor V out divided by the phasor V in, that's the voltage gain, as a function of omega. So if we look specifically at this circuit, we have a magnetically coupled circuit here. We'll call this a transformer. Our V1 then at the input to our circuit is 10 angle 0 degrees, and we'll let that frequency change. Omega is equal to some value of omega. And we want to find V out, which in this case is labeled as V2, the voltage across the 400 ohm resistor. So clearly that's just going to be equal to 400 times this I2, or phasor I2 current, the current in this secondary circuit. We'll call this the secondary mesh. Notice there's no electrical forcing function on this side of the circuit. This current is only forced by the magnetic coupling of these two inductors here. So what we need to do then is find that current I2, and so we can write our mesh equations, and this time we'll write them in terms of frequency. So we have I1 flowing through 1 plus j omega 1 ohms, and we'll write that as 1 plus j omega 1 times I1, and we see the mutually induced voltage, or magnetically induced voltage, will have a positive at the bottom, at the non-dotted terminal here. So in the direction of our mesh, that's negative. So we'll subtract our j omega. The mutual inductance is 9, so j omega 9 times I2. And that will all be equal to our voltage phasor here, V1. And then in our secondary mesh, we have I2 flowing through in a clockwise direction, j omega 100 henries plus 400 ohms, and we have so that's times our I2. In our magnetically induced voltage here, we'll have the positive reference. Since I1 is flowing into the dot, it'll appear at the dot. We'll have the positive reference of our mutually induced voltage, and in the direction of our mesh current, that would be negative because we'd have the plus at the bottom, so we subtract that. So both of our mutually coupled or mutually induced voltages are in the negative direction for our mesh equations. So we want to then solve this for I2, because that's what we want to get, is the ratio of the voltage phasors, and by substitution we can get I2 in terms of omega, where what we have is a second order polynomial with respect to omega in the denominator, and a first order linear omega times j90 in the numerator. So we do have a complex current there, which we could be represented in both rectangular or angular form or polar form if we had a value for omega. So when we go and solve that, then we plug that in, we get our V2 over V1, we get that voltage gain in terms of omega here. If we graph that, then we have our voltage gain versus our frequency omega, V2 over V1 on our vertical axis and omega on our horizontal axis. We can plug in, if omega is equal to 0, then we'll get a 0. If omega is equal to infinity, we can divide numerator and denominator by omega squared, and we see we'll have we will still get a 0. So our function is 0 at 0 and 0 as omega approaches infinity. If we want to find the maximum voltage gain with respect to omega, then we'd have to take the first derivative of this with respect to omega and solve for omega. We'll end up solving for omega being plus or minus j something. So omega will turn out to be an imaginary number, and we'll find out more about that in the next module where we'll analyze the S-plane. But then we could still find the frequency at which we get a maximum and plug that back in and get our maximum value. So additionally, we've introduced in this video the concept of a transfer function and voltage gain, which we'll also look at more in further modules. However, notice what we've done here is a frequency sweep. So a frequency sweep is something that we also do in PSpice. Typically what we've done up to this point is we've plugged in a specific value for frequency, but if we want to do a frequency sweep, then we have to consider our inductances j omega L and our capacitances 1 over j omega L for their impedances. So that's all for this video.